Good evening, friends. My name is Manoj Khati. On behalf of ASHRAE Rajasthan chapter, I invite all of you to attend this webinar. This webinar is being organized by 3 chapters jointly of ASHRAE. ASHRAE Rajasthan chapter, ASHRAE Bangladesh chapter, and ASHRAE Chennai chapter. We thank you all, ASHRAE 3 chapters, for hosting this wonderful webinar. Before we start this webinar, I would like to read out the ASHRAE Code of Ethics. In this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflict of interest. Now, I would like to introduce the speaker of the evening. Our speaker for today evening, Mr. Jerry Day, is from Singapore, will deliver this webinar on airflow measurement, particularly focusing on thermal dispersion as a measurement technology. He is a founding member of IAQA chapter in Singapore, and he is also an active member of ASHRAE Singapore. He is associated with Eptron and represents them in Southeast Asia. He has been associated with many projects, particularly in healthcare segment, in the hospital area, green building, assisting them in designing good airflow measurement system. Now let's hear from our speaker, Mr. Jerry Tay. Mr. Jerry, we invite you to deliver this webinar.
Thank you, Mr. Manoj. Can you hear me?
Yes, Mr. Jerry, I can hear you.
Right.
I am inviting you as a presenter.
Okay, let me show my screen. Okay, so thank you, Mr. Manoj. Good evening, everyone. Thank you for your time to join us on this webinar. And thank you very much for the opportunity from the ASHRAE chapters. Hope everyone is doing well and staying safe. Okay, I'm Jerry. I'm from Singapore. Likewise, we also had a lockdown here, but we did not call it a lockdown. Okay, interestingly, our government, we call it a circuit breaker. Right? I guess different countries call it a different thing. What I heard is that the minister in charge of the task force, okay, he was an electrical engineer. So I guess circuit breaker was probably his idea, right? So our company, we represent Eptron from the US for their thermal dispersion airflow measurement systems, right? Eptron has been around for more than 35 years. And almost all of what they do in these 35 years is just airflow measurement and developing their thermal dispersion technology. In fact, Eptron is the one that created and coined this term thermal dispersion, right? So today I want to discuss understanding direct airflow measurement. So some of you may be wondering right now, why is this even a topic worth your time here, right? So isn't direct airflow measurement simply means measuring airflow directly? Okay, so what's there to talk about? Okay, but surprisingly, this is actually one of the least understood areas in our HVAC industry. right? So very often resulting in a misapplication of equipment and control strategies. All right. Okay, so first, I would like to start with some questions. Okay, when we want to control temperature, just temperature, so what do we need to do first? We need to measure, right? Likewise, for water, to control water flow, we need to measure water flow as well. Same for almost all other parameters. But what about airflow rate? What do we do to control airflow? Okay, it seems pretty obvious now. We need to measure. But are we really doing that? Instead, we use things like static pressure, damper positioning, temperature mass balancing, or in the case of outdoor air, we use CO2. So all these are what we call indirect measurement and controls. So why are we not using direct airflow measurement? Okay, one reason is this. Airflow is perhaps one of the hardest parameter to measure. Why? Because of the compressibility of air, turbulence, velocity profile, etc. And on top of that, there hasn't been many reliable technology to help you with that either. Okay, but today I can tell you that that is not the case anymore. There are equipment that can give you reliable and accurate direct airflow measurement. Okay, you cannot manage what you cannot measure. Okay, I'm sure you have seen this quote a lot. So when you don't measure, you have a lot of uncertainties. And then what happens? You have to put in a lot of safety margins, safety factors. Your equipment, your AHU ductwork, your VAV boxes, etc., will tend to be oversized. And then cascading backwards results in your water side equipment being oversized as well. Okay, so if you know that you can measure airflow reliably, okay, it's very likely that you can size your equipment accurately. Imagine the kind of first cost you can save. Not only first cost, but operating costs as well, because your equipment can now run at a much higher efficiency, saving you energy and improve your equipment lifespan as well. So how does an accurate airflow measurement save you energy, and by how much? Okay, you might ask. Okay, there are a few ways to look at this. Okay, one way, okay, think in terms of the third fan law. Fan speed, it has a cubic effect on power. So just a 10% reduction of fan speed, right, is going to give you about 30% of fan energy saving. 20% is going to give you about 50% saving. Okay, that is a lot. So, and the payback period of using a good permanent airflow device is just a few months, especially for big facilities like an airport that is running 24 hours. Okay, you can do your own calculations on that. So today I'm going to show you what are the airflow measurement technologies available, and more importantly, the differences between them. Right, so this is the direct airflow measurement device that I was referring to. Okay, for simplicity, let's just call it an airflow station. So an airflow station, it basically just measures and provides your building automation system with a real-time continuous reading of airflow velocity or airflow volume. So in a conventional AHU system like this, okay, you can measure at these locations: outside air, return air duct, supply air duct, or even exhaust air duct, giving you different applications. Okay, before I carry on further, I understand that there are many of you doing pharmaceutical projects, clean rooms, laboratories, etc. So I just want to show you these project references to start off. Right, most of the big names had already been using thermal dispersion technology for many years, right, including US FDA themselves. Okay, these are just some clean room projects in 2017. Right. However, thermal dispersion airflow stations, okay, they are not just for clean rooms. They are used very widely in commercial buildings, schools, research institute, and other general applications. Okay, so I'm going to talk about two parts here today. The first part is about the why and the where to measure this airflow. Okay, basically is talking about the applications. So this will be fundamental to many of you. So please bear with me. But the reason I need to talk about them is because I need to bring the focus of these applications towards direct airflow measurement. In the past, these applications may not be using direct airflow measurement, but indirect methods. Then the second part will be the how to measure this airflow. So basically, I'm introducing the airflow technologies. And this part here is important. Okay, for example, okay, let's say we don't talk about airflow station. We talk about laptop. A laptop for your building automation system, your BMS. Okay, whether you choose Lenovo, Asus, or Dell, it doesn't make too much difference today. Because why? Because the technology for a laptop is more or less saturated or mature. Any of these will meet your need sufficiently. Okay, but this is not the case for airflow stations. For an airflow station, different brands, different technologies, they perform very, very differently. So you have to be very careful with what you are selecting as your airflow station. So later on, we're going to show you some performance data as well. Okay, for supply air. Okay, in certain applications, we talk about air change rate or air change per hour. Same thing, it requires the measurement of supply air. Traditionally, we engage a system balancer to manually measure the supply airflow, or we use tracer gas methods. Okay, but these measurements are what I call one moment in time, because the next moment, some conditions change, and the airflow value that you measured a while ago is not valid anymore. And there are many factors that can affect your AHU output over time. Okay, for example, filter loading, or air leakages, or pressure changes, etc. Right, this will change your supply air output, even if your fan is running at the same speed. So since you're going to spend money on doing the manual measurement, so why not invest in a reliable permanent airflow station that can give you continuous measurement anytime you want? Right, the keyword here is reliable. If the airflow station is not reliable, it's going to give you more problems than you start with. So with this reliable and verifiable continuous measurement, okay, these factors, okay, they don't matter anymore. Okay, you can determine anytime if your design is working as expected, or even go back in time during your troubleshooting. And then you are able to show evidence that there's nothing wrong with your HVAC system that could have affected your production quality control, for example. Right, the next one, supply air and return air. Okay, this is more for room pressurization. Okay, one example here. Okay, this is showing a positive isolation room. Okay, it is very important for a stable pressure control in such an application due to the health hazards involved if not controlled properly. So traditionally, we will use static pressure to control the room pressure. So we can see what happens when the door is open and closed. So when the door opens, okay, the system will detect a drop in your room pressure. And then we'll try to compensate by increasing the pressurization flow or airflow differential, okay, to try to increase the room pressure. Okay, in this case, the pressurization flow is supply air minus return air. Okay, and when the door closes, okay, the room pressure will shoot up due to the excessive airflow. Then the system will hence try to compensate by reducing this pressurization flow drastically until there's a point in time that it overshoots and the isolation room pressure goes below zero. So this is very dangerous as it allows contaminants that are already lurking at the boundary to actually cross that boundary and enter that isolation room. Okay, so this is for static pressure control. So instead of using static pressure as a control, we recommend using airflow differential, okay, between your supply and return as a form of airflow control. So some of you may know this method as volumetric tracking or airflow tracking. The differential reading between two airflow stations, okay, here and here, right, will provide the required positive pressure, right? So basically, if you need a higher pressure, you simply increase the airflow differential. Okay, so you can see when the door open and close, the pressurization flow will maintain the same, and the lowest the pressure will go is 0. It will never go to negative. Right, we take a closer look. Right, so okay, let's say we use a static pressure sensor for this single pressure zone. Where do you locate this static pressure sensor? Okay, we know that finding a good place to install the static pressure sensor is always a problem, and the responses are very erratic. Okay, it is hard to do a proper control using static pressure. But if you use airflow as control, it will be much more stable and predictable. Okay. For airflow control, very simply, yeah, you measure the supply air and the return air using precision airflow stations, and then you maintain a small differential flow between these two readings. Okay, for example, we maintain 100,000 here, 90,000 here, and that difference of 10,000 cmH, okay, will ensure a very stable positive pressure in your single pressure zone. Okay, so this is the airflow tracking method. But with this method, there's one important thing to note. Okay, you need accurate airflow stations to do a proper pressure control, right? Okay, now let's see. Imagine you are using a certain brand, okay, X, with a plus minus 10% accuracy. Okay, in terms of airflow, 10% seems quite acceptable. Okay, but let's see what happens here. Okay, your airflow device is showing 100,000 here, but in actual fact, the actual airflow inside is only 90,000. Likewise, for return air, okay, the device, your airflow device is showing 90,000, but the actual airflow inside is 99,000. So when you look at these two display here, you are expecting a 10K and then a positive pressure, but instead you are getting a negative pressure. Right? So what happened? It's because of this accuracy. So research calculations have showed that for this method to work well, you need an airflow station with a plus minus 3% accuracy. Okay, the third application, outdoor air. I spent the last 10 years talking to people about the importance of ventilation, right? But I understand because ventilation, air, is intangible and it doesn't exactly have an immediate effect on people. So it has never been a priority for most until now. And it took a pandemic for the public to realize that. Okay, so this is actually a very hot topic nowadays, recently in the past 2-3 months. Okay, outdoor air measurement, they look something like this using an airflow station. Okay, so why do we need outdoor air to come into a building? Okay, mainly it is for the dilution of indoor contaminants, such as the VOCs, or what we call volatile organic compounds, and bacteria, molds, viruses, etc. Right, and to protect the contaminants from this, to protect the occupant from these contaminants in an indoor environment. So in a pandemic, we talk about viral load, okay, which is a concentration of the virus that can trigger a cluster spread of the disease. So it is critical that we dilute this concentration out by introducing outside air into an indoor environment. So how much outdoor air to bring in is considered sufficient? Okay, most would use this ASHRAE 62.1 as a guideline, okay, based on the number of occupants and the floor area. Right, I'm sure many of you are familiar with this standard. Okay, but take note, ASHRAE 62.1 is a minimum guideline. So during this pandemic, we might want to seriously consider increasing the ventilation rates beyond this minimum guideline. Sadly, even before the pandemic, minimum ventilation rates are often not met. Okay, in the next few slides, I will discuss briefly why this is so. Okay, and recently we can find a lot of articles that argues whether the spread of virus can be propagated by a HVAC system. So we see many cases like the Princess Diamond cruise ship in Japan, or the restaurant in Guangzhou, etc. And just recently, I saw an article on LinkedIn by Dr. William Bumflet, who is an ex-president of ASHRAE. Okay, you should be able to find his post in LinkedIn. So according to his article, okay, there was this cluster spread in this Guangzhou restaurant, which is now famous. So researchers went in, they investigated using tracer gas and CFD. So some observations, okay, the restaurant was poorly ventilated with mainly recirculating air, and then most of the exhaust fans were not working. And the ventilation rate is only at 1 liter per second per person, instead of the minimum requirement of 7. Okay, this is another article saw recently as well. Lawrence Berkeley National Labs is conducting research into the relationship between airborne virus transmission and quote unquote normal ventilation, extra ventilation, or extra filtration. So, and by the way, Flex Lab, they are using Flex Lab, which is a rotating lab, and they are actually using thermal dispersion, airflow station, as their basis of measurement. So another article here, okay, which was published, I believe, just a few days ago. I saw this yesterday, right? Also co-written by Dr. William Bumflet. So it's describing ventilation playing a critical role in removing exhaled virus-laden air, thus lowering the overall concentration and therefore any subsequent dose inhaled by the occupants. So how many of you right now can safely say that the building you are working in or the projects you have worked on in the past are having sufficient ventilation? With the lockdown gradually being lifted in the coming months, do we want to have a peace of mind as we go back into our office to work, or shopping malls and restaurants to enjoy some family time, knowing that ventilation is not going to be a problem? In a lot of articles, it is very easy to say open outside air dampers 100%, or open windows in office building, etc. But we cannot do that here in Singapore. I believe likewise in India as well. The energy consumption and the unfiltered outside air entering are going to create new problems. So you can see there needs to be a balance between having sufficient ventilation and energy consumption. Under ventilation, it affects your indoor air quality and increased risk of virus spread. But the energy cost of over-ventilation, okay, is just too much for certain climates. And let's not forget, while fighting the pandemic, okay, which is going to be a long fight, by the way, okay, we are still fighting the war against climate change, okay, where time is already running out. So how do you maintain sufficient ventilation without wasting too much energy? Measure your outdoor air intake. Okay, it sounds simple, but it is not straightforward. Okay, so calculating the amount of outdoor air to bring in using the ASHRAE 62.1, okay, that is the easy part. Okay, but ensuring this amount of outdoor air that you just calculated is being brought into your breathing zone, that is the difficult part. Traditionally, there are some methods of determining how much outdoor air that is coming in. So these are, for example, fixed position intake damper, temperature mass balancing, delta CFM, or even CO2 demand control ventilation. Okay, I have some, however, there have been some researches done over the years, okay, most notably from Lawrence Berkeley National Labs, that these methods give more than 60% error. I have some papers that describe in detail the issues with ensuring ventilation. Okay, if you're interested, please email me or Mr. Manoj and we will send them to you. Okay, let me just show one example of why these methods have such a high error rate. Okay, let's look at one, fixed position intake damper. Okay, let's say we are commissioning this system using fixed position damper method. And on this day, there is a head-on wind and we are manually measuring the outdoor air volume. Okay, We will then adjust the damper until we get the outdoor air volume that we want. So what happens next? We assume that for the rest of the year, we will have this amount of outdoor air coming in for our occupants. And just on the next day, instead of head-on wind, you have a crosswind. So what is the amount of outdoor air that's going to come in today based on that fixed position damper? We do not know. Okay. Worst case, when we have a leeward wind coming from behind, right? We have done tests actually that showed that instead of air going in, we actually have air exhausting out of your system. So without continuous measurement, we simply do not know. And this wind effect is just one of the many effects that contributes to these high error rates of these traditional methods. Thankfully, there are green building standards to take care of this. ASHRAE 189.1, okay, which is the ASHRAE standard for green buildings, and together with LEED, and this agreement is from Singapore. Okay, all these, they have this criteria that requires the installation of direct airflow measurement device to monitor the outdoor air intake. Okay, we look at LEED 2009. This criteria, during that time, it was only an optional credit. But in 2013, LEED V4, it became a prerequisite. So it goes to show the importance of this criteria of installing airflow measurement device. So this is for LEED V4, for those who are doing LEED projects. So it's a prerequisite now. So you have to provide this direct outdoor airflow measurement device capable of measuring the minimum outdoor air intake flow, and with accuracy of plus minus 10% of design minimum outdoor airflow rate. Okay, this accuracy of plus minus 10% of outdoor air is actually not easy to achieve. And most airflow stations in the market are not capable of this accuracy. Right, I'll go into more details later on when I introduce the different technologies. Okay, the second part here, as I mentioned earlier, this is important because it's unlike equipment where the technologies are saturated or matured. For an airflow station, okay, different brands, different technologies, they can result in very different performance in the field, right? So, yeah, I mentioned I'm going to show some data of this performance. Of course, you don't have to take my word for it. All the tests and experiment data that I'll be showing, okay, you can actually replicate them yourself to show similar results. Okay, for direct airflow measurement, okay, I have classified this device under two main categories. The manual device, which are handheld, and they are usually single point device. Okay, then manual device, you have this pitot tube, hot wire, which are commonly used by the professionals or system balancers. So there are other things like vane and propeller anemometers, flow hood, etc. Okay, on the right side, you have multi-point airflow stations, okay, which are permanently installed. Okay, so you have this Pitot Array, which many of you may have used before. Pitot Array have been around for a long time. Okay, it is simply a manifold of tubes with very small holes. And then you have this thermal dispersion, and then some uncommon ones. Okay, somewhere in between these two categories, okay, there is this device called the air velocity sensor. Okay, it is a single point device, but it is permanently installed. Right, next few slides, I'm going to show you some things you should take note of when using this air velocity sensor for airflow measurement in the duct. Okay, okay, there's this thing called velocity profile. As air, when it moves in a duct and passes through a disturbance, okay, it creates this velocity profile. Okay, this is a disturbance here. In this case, it's a centrifugal fan. Right, this could be a fan, it could be an elbow. Right, and in this case, okay, the velocity of the air particles in the center of the duct is fast. Okay, while the particles near the duct wall is slow because of duct wall friction. So now imagine if you use a single point air velocity sensor to measure just one point in the center of the duct, you will be getting a false reading. And this is why to get a good airflow reading, we need to take multiple points or samplings across the duct cross-sectional area and get an average reading. And that is why we have multi-point averaging airflow stations like this, okay, multiple points. So you can see here for velocity profile, for different upstream disturbance, like in this case for an axial fan, this is a centrifugal fan. So an axial fan, it creates a very different velocity profile, right? So it's very hard to predict velocity profile. So for third-party system balancers, professionals like NABB, okay, when they do manual measurement on site, they follow ASHRAE guidelines and they take multiple points using like pitot tube or hot wire. They take multiple points and they get an average reading. So this is how it should be done. So likewise for permanent mounted airflow stations, you need multiple point sensors. So many project specifications for permanent airflow measurement device are very generic. And what happens is that the project will end up getting a single point sensor to measure airflow in the duct. So no matter how good this single point sensor is, you will never get a good reading without taking a multiple point average. Okay, to really drive this point across, okay, a few years ago, I did this duct traverse together with MCAR at their wind tunnel lab. So we set up this centrifugal fan and 550 mm duct work, and then we use a TSI hot wire. We measured 25 points across. Okay, the wind tunnel, because it's a wind tunnel, so we set the reference, we fix it at 10 meters per second. So these are the 25 points measured with the tunnel reference set at 10 meters per second. You can actually see the velocity profile here. Okay, with some as low as 8.05 at the top right end or 14.9 at the bottom. Okay, so this is the velocity profile you can see. So this 25 points average is 10.45. So it's about a 5% deviation from the wind tunnel reference. Okay, which is actually quite good for a manual measurement, 5% off. But now imagine using a single point air velocity sensor, okay, which measures only 1 point. The deviation in this case is more than 30% off, right? So for airflow measurement in a duct or outdoor air intake, okay, we always recommend multiple point averaging instead of single point, unless the duct is really very small, such that you cannot have at least a 2-point sensor for averaging. Okay, so we are going to look at the multi-point airflow stations. Okay, mainly the Pitot Array and the thermal dispersion. Okay, Pitot Array is actually simply a manifold or pipe with many small holes like this to pick up total pressure and static pressure. Okay, and then the velocity pressure is then derived and output as velocity using the pressure transducer. So there are several form factors for Pitot Array. It can look like this, right, or insertion probe, and this cross flow sensor inside a VAV box. Okay, that is a Pitot Array as well. I'm sure most of you are familiar with this. So you should know that because of the small holes, okay, they tend to clog up very quickly. And some other issues include averaging error, sensor drift, and rotation effects, okay, that can significantly affect the accuracy of a Pitot Array. Okay, the next one is called Vortex Shading. Okay, this technology is very uncommon in commercial HVAC systems. So I will not go into details about this technology, other than the fact that I also don't really know much about it. Okay, I have seen it, but I have not operated it before. And all I know is that this type of airflow station, it makes use of a phenomenon called vortex shading. So as the wind blows over a round body, it creates vortices and in turn pressure pulse. And these pressure pulses are picked up by a microphone and is then translated to airflow velocity by a transducer. So there are many limitations to using this technology in a commercial setting. Therefore, it's not common and it's very expensive as well. Okay, the next technology is called thermal dispersion. The term thermal dispersion is actually coined by a manufacturer from more than 35 years ago. And right now you may see other brands calling themselves thermal dispersion as well, but they are not the same, and they may differ a lot in performance. So what you see here is thermal dispersion insertion probe that currently has 4 sensors. Okay, these black dots here, these are 4 sensors, and depending on the duct size, okay, there could be more than 1 probe, and between 1 to 8 sensors per probe. The idea is to have sensors spaced across the duct area for sampling. And these are independent sensors, okay, meaning they each measure their own air velocity at their location. So for this particular manufacturer, each sensor has 2 glass-beaded thermistors. These thermistors are high-end thermistors that are designed for and used by NASA, and also used in biohard catheters. They are encapsulated in glass. They are therefore very stable and not subject to the elements. So one of the thermistors is an ambient temperature sensing thermistors, okay, while the other is a self-heated thermistor. Self-heated meaning current is passed through it from the transmitter to heat it up. So as air passes through, heat is taken away from these thermistors. Hence, the delta T, or the change in temperature between these 2 thermistors, will change. Okay, so knowing the relationship between delta T and the power, we can actually work out what is the airflow velocity that is passing through, right? So this technology, in fact, has a very high accuracy and precision, not just in airflow, but mass flow as well. So the airflow station from this manufacturer, it has a published accuracy of ±2% of reading, right? I underline here of reading. Okay, this is very important to distinguish from other technologies. Okay, I'll explain in a moment. Okay, because this uses thermistors, it has a second output of temperature as well, with an accuracy of ±0.08 degrees Celsius. This temperature is velocity weighted average. Okay, both these readings are with NIST traceability. NIST is the National Institute of Standards and Technology in the US. Okay, they are the authority in terms of measurement. So normally you will see NIST traceability only in primary or calibration equipment. Yet this manufacturer has NIST traceability in every sensor that they produce. Okay, just now I mentioned this percent of reading in terms of the accuracy. Okay, for a pressure device like the Pitot Array, okay, what it has is so-called percent of full scale. Okay, and it's very different from what thermal dispersion have percent of reading. For example, the Pitot Array, okay, or rather the pressure transducer. Okay, let's say it has an equivalent full scale of 10,000 cmH. Okay, and then we are measuring a duct where the actual reading is 1,000 cmH. A Pitot Array system that publish itself as ±2%. Okay, what it normally means is ±2% of full scale. So 2% of full scale is 2% of this value here. So you can see as it propagates down, the absolute error may end up with ±20%. But as for her thermal dispersion, it's a percent of reading. So a 2% of reading is a 2% of this value here, 1,000. Okay, the absolute error is ±2%. So you can see the difference. So that's why you have to be very careful in selection when it comes to accuracy. Because a Pitot Array normally they only tell you they are ±1% or ±2%. That's all. So you will know that it actually means a percent of full scale. Right. This is a technology overview for different types of airflow stations. So in particular, you look at outdoor air intake, where the velocity is typically low, usually about 2.5 meters per second and below. So if you are doing lead projects, please take note. Okay, only thermal dispersion is able to measure this low flow effectively. So many of you may have experience with using pressure-based, maybe it's Pitot tube or Pitot Array, for example. So when your airflow is below 2 or 2.5 meters per second, what happens? Okay, you will get an error. Okay, your display will show an error. And the reason is because of this. Okay, the Pitot Array, this is a Pitot Array signal curve. Right, over here, this horizontal axis is airflow, the vertical axis is sensor output. Okay, so this is essentially a pressure curve. At the low end, where the outdoor air is normally at, the Pitot array can only provide a small signal. Okay, and most of the time, the transducer is not able to give any reading at all at this end. Signal amplification may not work well here because if you use signal amplification for such a small signal, okay, you amplify noise as well. For thermal dispersion, okay, this is the natural curve. Okay, for any change in airflow, you will have a very big signal change. Therefore, the resolution is very high, especially at the low end where the outdoor air is concerned. Okay, this is from the X-ray handbook. Okay, this is you can look at Pitot array. It is stated that for Pitot array, the range is between 3 to 50 meters per second. So anything below 3 meters per second is not recommended to use a Pitot array. Therefore, most outdoor air application is out. Also for accuracy, okay, it is plus minus 2 to greater than 40% of reading. All right, there are some limitations described here as well. The averaging error, it must be kept clean and it needs to be field calibrated to a handheld reference. Okay. For thermal dispersion, the range is almost 0 to 50 meters per second, and the accuracy is plus minus 2 to 10% in general. Okay, next, maintenance. Maintenance of equipment is always a concern for many, especially those on the ground. Okay, so this slide describes a military standard test of blowing dust at a Pitot array and some thermal dispersion sensor. And this is the result after just a few minutes of exposure to dust. So those who had used Pitot array or VAV cross-flow sensors will know, okay, they get clogged up very fast. For thermal dispersion, okay, it is a big through hole. They do not get clogged up. Okay, and for particular manufacturer, the thermistors, they are glass encapsulated. So that means they are very smooth and it doesn't trap dirt easily. Most of the projects that are using thermal dispersion, they did not have to do any maintenance at all for many years. Okay, even though we do recommend checking them every year or so. And if needed, okay, cleaning is very simple. It's just using a brush or compressed air, that's all. Okay, when we talk about sensors, we always talk about sensor drift, right? So this particular manufacturer, they have tested their thermistors for more than 10 years to show only less than plus minus 1% drift, okay, over 10 years. So what this means is that periodic calibration is not required. Okay, I know that in certain industry, periodic calibration is a big headache, right? And not only that, these sensors, they are factory calibrated with niche traceability, meaning you do not need to perform site calibration. So this thing is almost like plug and play. So you save the engineers and contractors a lot of time and trouble so that they can actually focus on other urgent matters. Okay, in terms of airflow stations, we have this test called the elbow test. I actually have a video on this test, but I don't think I have the time to show here. Okay, so we run the fan at a constant speed. Okay, and then we will insert an airflow station, okay, at 5 locations, okay, which is this reference point, and then we will shift to other 4 locations, 1, 2, 3, and 4. Okay, and then we record the airflow values. So the reference position that you see here is where the airflow is actually fully developed after a long straight up run. Okay, and this is actually the best place to measure airflow, regardless of whichever airflow technology. So we do this test for both types of technology, thermal dispersion and Pitot array. You can see that, okay, this is a result. You can see that for position 3, okay, which is immediately after an unveined elbow, okay, this is probably the worst place to measure airflow because there's a lot of turbulence here. And for the Pitot array, you can see that it deviates from its reference reading by about 45%. Take note, it's the same sensor. They are just measuring at different location, but it's giving you this type of deviation. And this is despite the fact that for this Pitot array test, we are using a USD $2,000 MKS Baratron transducer. It's a lab grade transducer, not the typical low-cost transducer that is commonly used in the field. Okay, for a thermal dispersion, even at this kind of poor location, okay, this particular manufacturer can still get about 5.6% deviation only. Okay, so the significance of this test is that in the real world, okay, we seldom get this kind of long straight duct run in our AHU room, right? Okay, I'm very sure of that in Singapore, yeah. And more often than not, the duct turns or branches out immediately after the outlet. So when you use thermal dispersion, you actually have a peace of mind that even in the worst condition, you still get a reading that you can actually use. All right, I'm down to my conclusion. As I've shown, different airflow technologies, they result in very different performance. So you have to be aware of what type of airflow device you're going to use in your project. Even for the same technology, performance can differ between brands. So if a project specification for airflow sensor is very vague or very generic, it's likely a single point air velocity sensor will be used. So no matter how good this single point sensor is, you will never get an accurate duct flow reading. Okay, nothing wrong with the sensor. Okay, it could be the most accurate sensor in the world, but it's just because the methodology is just wrong. Okay, mainly because of the velocity profile. Okay, if the project specification calls for a multi-point airflow station, okay, you may end up with a Pitot Array. Okay, remember, you have to perform site calibration for every single Pitot Array installed. You have to perform periodic calibration and periodic maintenance as well. Okay, it costs a lot of time and money. And let's not forget the accuracy uncertainties when you use a pressure-based device. Okay, lastly, some tips on selecting a thermal dispersion device. Okay, make sure that the niche traceability calibration is not just for temperature alone. Okay, it has to be for both airflow and temperature to make sense. Sensors should be individually serialized and calibrated, okay, to eliminate the individual thermistor's unique characteristic. Okay, one last thing, whichever airflow technology you use, it is important to know the kind of technical support you can get from the manufacturer or supplier, because where you install the airflow station in a ductwork is very critical. Make sure a supplier can actually help you to find the best place to locate every single airflow stations for the best